Alright, well welcome to POLS3025. This is a regression example for week 11, and what I'm going to do today is I'm going to go through a complete analysis using some data running from descriptive statistics all the way up to multiple regression. So let's get started, and I'll begin by opening Stata. Please note that I'm using a Mac, but the commands work just as well on a PC if you happen to be using a PC. So let's open Stata. And I'll put this onto here, make it nice and big so everybody can see. And as you can see here, we have the Stata interface. This is version 15 up here, but that doesn't matter. The commands and the interface are almost identical to Stata version 14. So the first thing we're going to do is we're going to open up a new do file. I'm going to do this with File, Do File, and the Do File editor opens up on the main window. Now, as I've indicated in my own tutorials, I think it's a really good idea to start building your models by editing in the do file rather than noodling around in the command line and in the command editor down here. So we'll start off by getting a good do file going by following some basic principles. And the first thing that we should do is we should set up some comments informing people what exactly it is that we are doing. So this is POLS 3025, week 11, regression example. Notice that I have a star in front of the line, which tells Stata that this is a comment and that it should ignore anything that follows the asterisks. That is not a command, it's just a note to myself. I'm also going to make note of what my dependent variable is and my independent variable. Now the research question that I'm interested in here is I'm actually interested in exploring the variation in vote shares that MPs have in Canadian federal elections. Those are MPs that are incumbents. And the reason I'm interested in this is because Canada sticks out in some ways, insofar as that there's very high levels of turnover. And so I'm interested in exploring whether or not maybe there's a relationship here with vote shares that incumbents simply don't win very big, and there's not a lot of an incumbency effect going on here. There are other elements to that study that could be examined, but we're going to start just by looking at vote shares. So the dependent variable in the study is going to be vote shares. And the independent variable, which I'm going to explore, I've got a couple of things in mind, is incumbency. So independent variable 1 is going to be incumbency. And I'm going to measure this particularly using a variable that records how many elections an MP has won beforehand. I'm also interested in whether or not MPs have switched parties, because typically we associate party switching with losing vote shares. So those people who don't resign before the next election after they've switched parties, we expect them not to do very well in the next election because of the high party association that Canadian voters have. They don't think too much about MPs themselves, but they are attached to political parties. So independent variable 2 will be party switching. Okay, then we can make this a little more explicit in our do file by putting out the research question. And our research question is, what explains the variation in vote shares in Canadian federal elections? There's a null hypothesis, of course. And the null hypothesis is that there is no difference in vote shares between incumbents and first-time winners. And the alternative hypothesis for that particular statement is that there is a difference in vote shares between incumbents and first-time winners. Okay, and then we'll come up with some other hypotheses to look at later on for party switching if we want to. Now, at the beginning of all good do files, we should have some boilerplate. And the boilerplate that I always include is the version number. We need to clean up the data set insofar as we need to clear the buffer, clear out all data that might already be running in Stata at that time, so clear all. I like to set more off because I don't like the buffer to stop when I'm running a do file, and I write capture log close just in case a log happens to be running at that time. So that's our boilerplate. We should also set a working directory. And in this case, I can't exactly remember where my working directory is, so I'm just going to go up and find it. And if I look in my Dropbox down to, oh, here we go, datasets, I know that my dataset is in that particular folder, so I just choose the folder that I want. Down here on the results window is an echo of the command, so I'm just going to cut and paste that into my do file. So there's my working directory. Next up, I need to open up the dataset. Now you can open the dataset using File and Open, and you can locate the file and double click on it, and that will open it. But I also, because we've set the working directory already, it's going to look by default in that directory, and I happen to know that the dataset that I'm using is in there. So just the use command is the command that we can use to open up a dataset, and it's called POLS3025 week 11 example.dta. All right, good. So let's save the do file, and we'll save it as POLS 3025 week 11 example. It says I already have a file called this in here, so we will replace it with this new one. All right, let's run it. Here's the little play button, and it has opened up the data set. You can see that the variables in this particular data set have been opened up on the side here, so we can take a look at them. We have the echo of our commands up here, and I like to take a quick look at the data when it comes up just to see what it looks like. So what we have here is we've got a data set which consists of what looks like a unique identifier of some kind, a person GUID. Now, you wouldn't know what that is offhand, but what this is a database record that links these particular individuals to a Library of Parliament database in Canada. So even though the names of the candidates appear differently, even though they're the same person, in different instances here, they all refer to the same person. And this is the database identifier at the Library of Parliament. And then I have a separate identifier here, which is easier to type in than this big long thing called ID. We have the date of the election that they ran in, the number of the election that they ran in, the province where they ran, the riding, the party that they represented. You can see that these variables here are actually numerical variables which have labels. So the riding, so this particular field here for Acadia, which is in Nova Scotia, or no, in Alberta, beg your pardon, is coded as 6, but it has a label which is associated with 6, which identifies it as Acadia. And we have labels also for the provinces and for the parties. We have the number of votes that they won in the election, and then we have their vote share, and that's our dependent variable. That's what we're most interested in. We have a couple of other variables in there as well, which, whether or not they switched or not, that's going to be an important one for us later on. And then the nature of the switch that they had. Okay, so that gives us an idea of what the data set looks like. What we can also do now is we can decide to keep the variables that we need. This is a big long data set, as you can see here on the right, and we don't really need all of these variables, so why don't we just keep the variables that we want? And we can do this using the keep command. So I'm going to say keep ID, person guide, candidate, T, which is the date of the election number, whether or not the province that they're in, the riding, which is the constituency, the party that they're a member of, the number of votes that they got, their vote shares. Party prov share, which is the party. So let's do that again. Prov share. That's the share of the vote that the share of the seats that the party won in the MP's riding, in the MP's province. Pardon me. The MOV, which is the margin of victory, how much they won by. Elected, whether or not they were elected or not. Acclaimed, we'll see that this might be important later on, but did they run uncontested, and so did they just win by virtue of having nobody else to run against? Independent, were they an independent, so did they not have any type of party affiliation? Switched. And then I'm going to keep a couple of other things here. I'm going to keep policy office votes. These are the reasons for the switch, why they switched parties. There's also a variable here for next election, DNR, and that means that they did not run in the next election. We have an experience variable that records how much previous political experience they have. Female, are they a woman or a man? Their birth year, so we can calculate their date. Oops, what did I do there? And whether or not they were a cabinet minister, whether or not they were incumbent. Was it their first time elected? Because we want to know whether or not how incumbents fare against new winners. So first time elected and elections contested. How many elections did they run in beforehand? Okay, let's see if that works. There's a long string of variables there. I probably should have done this just by clicking on them. A neat trick in Stata is that if you need to break the line, you can just go 1, 2, 3 with front slash, and that will do sort of an invisible line break. So you can, without breaking the command, without causing the Stata to crash. There we go. That makes it look a little bit easier. So let's see if these variables now get put into the data set. I spelled independent wrong, so let's fix that. First time elected. Something wrong there. First time elected. Oh, I need another E. And there we go. And now we have reduced all of our variables down to this collection of variables that we're going to use or may use in our analysis. Okay, so now that we've reduced our variables, maybe it's a good idea to visualize and describe our data set. Okay, let's take a look at what we've got here. Well, the first thing we can do is we can describe the data set, right? So let's do describe. And we can see here that we've got all of the variables that are listed here on the right, and some variable labels. Some of them are missing. We don't have one for independent, and we have some value labels that are associated with each of these different variables. If we wanted to assign a variable label to independent, we could do that quite easily. We can simply say LA var independent, open quotation marks, independent. And that is now, as you can see here, assigned the label independent to the variable called independent. We'll cut and paste that and just put it into our do file. Okay, there we go. And assign a comment to that. There we go. Everybody's happy now. Good. Okay, what else can we do? Well, we should probably describe the data set in our do file. And we should summarize the data set in our do file as well. So we'll do describe and summarize the data. And we're going, because we're not putting any variables names after those commands, it's going to describe and summarize all of the variables in the data set. There we go. So in our describe, again, we have all of our names, all of our labels. There are 7,554 observations in the data set for 27 different variables, and the data set is 1.2 megs large. The data is sorted by ID and time, and when we look at the summarize command, we can see that there are obviously observations for all of our different variables. And we want to maybe take a quick look at vote share. Where's vote share? There it is. So here's vote share right here. And we can see that the mean value for vote share is 48. Well, in this case, it would be 48% because vote share is measured in percentage points. Okay, so let's take this a little bit further, and it's a good idea in our data set, in our do file, beg your pardon, to describe and summarize the dependent variable. So let's rerun this. And there we go. So there's our variable name. So its label indicates that it's vote share in percent. It's stored as a double, and the name is vote share, as you would expect. And if we summarize the variable, we can see that there is a mean value of 48.14 with a standard deviation of 11.75. The minimum value is 1.25, and the maximum value is 100%. As you can imagine, anybody who has 100% vote share is somebody who would have run uncontested and was claimed in the seat. Always a good idea to visualize the dependent variable as well. So let's visualize the dependent, visualize vote share. And we'll just do this with a histogram because it's a continuous variable. Okay, and I am going to superimpose a normal curve on top of that, and I'm going to store the graph into memory using the name command, or the name option, and I'm going to call the graph fig01, and I have to add comma replace after that, otherwise when the do file runs again, it's going to encounter the graph stashed in memory there. Okay, so let's, and we're also going to run so that'll be our histogram. Let's also run a box plot on that as well. And that's graph box vote share. And we're going to give that a name too. We're going to store it into memory. So we're going to go name, we're going to call it fig2, and replace. Okay, so let's see what we get here. There we go. There's our vote share, and that is a really nice normal distribution for vote share, with the mean centered there at around 48, which we know from our summarize command. And we can also look at a box plot of vote share, which you can imagine as being simply the vote share graph kind of turned on its side, showing where the concentration of data is located, primarily here in this interquartile range. There are the extreme ends of it, and there are some outliers on both sides. You would expect that given that it's such a large data set. So that's nice. Okay, so that means, of course, that with that normal graph, it means that we can think about using this particular variable in a t-test because it's nice and normal, and we can make some inferences based on this. So that makes our life considerably easier given that the data is already normally distributed. So why don't we just go ahead and do that? Okay, let's run that t-test. Now I'm going to comment these graphs out at the moment so that they don't continuously reload over and over again as we run the do files. But let's run a means comparison test. And the group that we're going to run it on is we're going to be interested in comparing it to incumbents versus non-incumbents. So we're interested in looking at the difference in vote share between those people who were elected for the first time versus those who were re-elected after the first time. So we're going to use the incumbent variable, which is a dichotomous variable. It's coded as 0 or 1, as the variable which demarcates our group, our comparative group, to compare the means with each other. Okay. So let's do this. We're going to do t-test, vote share, and we're going to do by, and then our group incumbent. And let's run this and see what happens. There we go. There's our vote, our t-test that comes out, and we can see that we have two groups: 0 for first time elected, and 1 for those who have been elected beforehand. And we can see that the means are actually very, very close, right? So 48 for the incumbents, and 48.15 for incumbents, and 48.12 for the non-incumbents, for the first-time winners. And we can see here that the difference between the two of them is minus 0.02, and that gives us a t of minus 0.10. And if we run our t-test to see whether or not there is a difference between the two of them, we find that the probability of getting this particular t from a distribution where there is no difference between the groups, the probability is 0.91, and that is not enough evidence for us to reject the null hypothesis that there is no difference between the two groups. So what we see here is that based on a simple t-test, there doesn't seem to be much of a difference in the vote shares between incumbents and first-time winners, maybe leading us to believe that really incumbency isn't helping you win by that much more as far as your share of the vote in your constituency in the election. We might also want to look at this a slightly different way. We might want to, rather than just sort of saying, using this very crude measure of 0 or 1 for incumbency, what we might prefer to do is look at the number of elections won. So moving from 1 and up to see, and we could think of this increase in elections as being categories, and so we might be able to run a chi-square test on this, or we most certainly can run a chi-square test on this. So let's run a chi-square test to see whether or not we see any difference between incumbents and non-incumbents based on how many elections the incumbents have run in. Okay, so we're going to do this with a chi-square test. So we're going to run a chi-square test on elections contested. So to do this, we just run a tabular analysis. So this is going to be on the elections contested variable, which simply records how many elections the MP has run in beforehand. And we're going to, for the second category, it's going to be a dichotomous category called elected, which simply records whether or not they were elected or not. Okay, and we're going to run a chi-square test analysis, and we're going to ask for the row and the column marginals and see what comes up. So let's run that and see what happens. Okay, well, this one's a little bit different. So here we can see that in our elections contested, we can see that there are some MPs that have contested up to 13 elections, not many, only 3. And we can see that of those 3, they won the elections. And so here we have elected equals 0 or 1. 0 is obviously that they were defeated. 1 is that they were elected. And what we can do here is we can basically take a look at whether or not the proportions of those MPs who were elected for each one of these elections contested is whether or not they're different or not. Okay, whether or not they are statistically significantly different from the null hypothesis that there should be no difference between the categories of 0 and 1 and the number of elections contested. Okay, and if we scroll down here, we can see that for a chi-square value of 709, when there are 12 degrees of freedom, there is a probability of 0.000, which indicates to us that we can reject the null hypothesis that there is no difference between these categories, okay, across the categories as well. So we're able to reject the null hypothesis, which then allows us to say that there are differences between those who win and lose elections, and the vote shares that they get as they accrue electoral experience. Okay, so that sort of says that maybe there's something more there than just looking at whether or not you are an incumbent or not. That actually, it's not just about whether or not you're an incumbent or not. It's actually about how many elections you have participated in. So there's something about the experience of elections that helps there. Maybe we'd want to take a little visualization of that to see what that kind of looks like. It might help us to make more sense of that in our heads if we can look at it. So we'll create we'll visualize that using graph bar. Whoops, let's visualize. So we can do graph bar, and actually before we do this, we're going to have to create an additional variable called defeated. Okay, and just so that we can compare those who won and those who did not win. By default, in the elected category, 0 equals defeated, but we're going to need to create the inverse of that variable, where defeated equals 1 and elected equals 0, just for graphing purposes. So we'll do gen defeated equals elected equals 0. Remember, you need the equals there when using conditionals, okay, and when you're trying to subset. Okay, so graph bar, we'll take the mean, then elected, so we want a bar for the proportion of those who were elected, and for those who were defeated, and we want this over elections contested. Okay, and then we'll call this figure 3. Just do fig 3 to keep it consistent. Replace. And I want to fix up the legend a little bit, because if you don't do this, the legend looks a little bit ugly. So I'm just going to do legend. This is just some formatting for the legend, and order 1 elected and 2 defeated. There we go. And what this is going to do is it's just going to format the legend so that rather than having elected equals 1 and defeated equals 1, we're going to have just elected and defeated as the legend labels. So let's see how this turns out. And there we go. Nice. Okay, so we can see that obviously in the very first election, when they are a newbie, they all win because they are not incumbents yet, so they've all won. And then as you go forward in time, you can see that, well, there does appear to be an increasing proportion of MPs who are winning elections, and the proportion of those who lose elections as they gain experience seems to decrease. So it's not very strong, but it does appear to be there. And what our chi-square test says is that the differences here across the number of elections that the MPs experience and the proportions of those who win and lose is different. Okay, so that's just a nice little visualization that we can use to help us make sense of what's going on there. Okay, so what's up now? What can we do now? Well, why don't we just see whether or not there's a correlation between our elections contested and vote share. Okay, so let's run a quick correlation. And the command for running a correlation is pwcore, which stands for pairwise correlation. And we'll do elections contested, and vote share. And we want to see whether or not there is a statistically significant relationship there. So we're going to type in sig after the command, after the comma, and we'll see what comes up here. I didn't want that to come back up again, so I'll just comment that out for future. And we can see here that there is almost a negligible correlation between vote share and elections accrued. The correlation is positive, but it is 0.055. It is a real correlation, okay? So it's not that we're, the statistical significant test tells us that it's real, but it is a very, very mild, bordering on negligible relationship there. Okay, so again, giving us some idea of the relationship between accumulating elections and how that relates to vote share. So now we'll go on to linear regression. And we'll start with bivariate linear regression. And we can use the regress command. Do vote share, which is our dependent variable, so it goes first, and elections contested. Okay, and let's see what happens here. And here we go. What do we have? Well, here comes our regression results. And if we look down here to elections contested, we can see that there is a coefficient of 0.37. So what this means, and the coefficient is statistically significant at the 0.05 level. It's 0.000, which is below 0.05, so we're able to reject the null hypothesis that the coefficient is 0, because of course the coefficient, recall, is a slope. So what we see here is that for every election that an MP adds to their election roster, they get a 0.37% increase in their vote share, which isn't a lot. This tells us that it's real, but the effect is very, very small. Okay, so it's not giving you a lot, but it gives you a very small amount. If we look to the R-squared, we could see that elections contested actually contributes very, very little to the overall variance in vote share itself. Okay. We can visualize this bivariate regression to get a better idea of how this is working. So let's do that. I'm going to do this using the pull down menus here, just because I find making graphs easier with the pull down menus. I could do this manually as well, but I think it's good for teaching purposes also to use the pull down menus every now and then. So we'll go to graphics, two-way, create. We're going to make a scatter plot. Okay, so there's the scatter plot, and we're going to do vote share for the y variable because that's our dependent variable, and we're going to do elections contested. That's our independent variable. We'll sort on the x-axis, and we'll say accept. Okay, nice. We're going to then add an additional overlaid graph on top of that. We're going to put the regression line on, so that's a fit plot, and we're going to put a linear prediction with confidence intervals. So we're just going to type in the same variables here, vote share and elections contested. Nice. Okay, accept. And just to make it look nice, we're going to add a title here. So I clicked on the title box, and we'll add bivariate regression of elections contested on vote share. Okay, looks good. Okay, we will run it, and there we go. We can see that the I beg your pardon. We can see that there are all of our elections contested, so 1, 2, 3, 4, 5, and so on. We have our vote shares going from our acclaimed individuals up here to people who just squeaked through, and quite a wide range on either side of those of that regression line, along that predictor line. The dots are kind of hard to make clear sense of, so we might think of trying to fix that up a little bit. And so what can we do here? Let's rerun that graphic, and we'll click two-way graph again. And for our scatter plot, we're going to edit the scatter plot, and we're going to change the dots by changing the marker properties. And instead of having the default dot, which is that black dot, we're going to pick a hollow circle. And it's a little bit big, so we're going to make them a little bit smaller. So we'll make them small. And then we'll go to advanced, and we're going to use a jitter on here. What does the jitter mean? The jitter just simply means that rather than having these dots line up exactly in a straight line, we're just going to allow them to randomly jitter around the values on the x-axis. So we'll add a noise factor there of, let's say, 2, and I happen to know that the outline width is better to see if you simply set it to thin. Okay, so let's click on accept, and we'll accept again, and we'll see that this graph actually becomes a little bit easier to read. There we go. Okay, so we can see that, actually down here at the lower values, there seems to be a much easier, it seems to be a higher concentration, obviously because most MPs don't last 13 years. But the values here seem to be quite nicely distributed around the regression line, which is nice to see. And yeah, so it's not a bad looking regression analysis. So, but one of the things we do see is that our regression line isn't exactly steep, right? It's running from down here to up here, and only very, very slowly increasing as you accrue more elections. Okay, so we know from our R-squared that the number of elections that an MP packs into their career as they pick them up doesn't seem to have much of an effect on vote share. So maybe we need to look for some other things that have an effect on vote share. So what I'm going to do is I'm going to add additional variables to the analysis. Now, in order to do this, I need to create a couple of new variables. And so what I will do is I will walk you through it, because that's really what I should be doing here. So let's make a multiple regression. Now I have a couple of ideas of what should be included in this model, and one of the things that should be included is we should account for the different types of parties that exist in the Canadian party system. And the reason we want to do this is because, of course, there are big parties and then there's little parties that, don't do very well, but maybe just squeak through. So we want to create a new variable that basically records whether or not you are an established party or not, or whether or not you are just a small one-person party that maybe was lucky and happened to be elected, or for that matter, even maybe a little bit bigger, but just was not one of the big parties that you typically associate with the Canadian party system. So let's make a new party label. So if we go to party here and we do, let's say, BR party, we can see that there are a bunch of different parties. There's the Progressive Conservative Party, the New Democratic Party, the Liberals, the Conservative Party, the Liberals, Progressive Conservatives, and so on. And then we have a couple of others that scatter around here. But if we tab party, we can see that really the big parties in the party system are obviously the Liberal Party, the Progressive Conservative Party, the NDP, the Bloc Québécois, the Conservative Party of Canada, and then a couple of other parties. The CCF was the predecessor to the NDP. But otherwise, we have a number of very, very small parties, and of course, a number of independents who ran as independents. So what we want to do is we want to basically take these big parties and group them together, and then create a dummy variable that indicates whether or not you are a member of a big party or not a member of a big party. So make a new party variable. And you might want to fast forward a little bit on this, on the on YouTube or on the video, simply because this is going to be a bit of me typing, creating this new party variable. And if you're comfortable making new variables, then just skip ahead a little bit. Otherwise, you can follow along here. So what we're going to do is we're going to start off by decoding the party variable. As you can see, party is actually a numerical variable. It's a numerical categorical variable which has labels assigned to it, and I can't really remember over and over again what the numbers are for these things, but I can remember what the labels are. So I am going to change the number into that label. So here, I'll show you how I'm going to do that. I'm going to use the decode command. So decode party, and then it's going to create a new variable called party alpha, just for the purposes of making this new variable. We're going to drop the old party variable, so we're going to erase it, and we're going to rename party A party. So that's our new party variable. Okay, and if we take a look at that, we would now see that if we do tab party, it's going to be the same. Okay, that's nice. But if we do br party, we can see that parties are now in red and that they are actually strings. They don't have numerical variables attached to them. And if we do de party, we will see that they're coded as a string. There we go. They're coded as a 10-character string. Or sorry, there we are, 10-character string. Okay. So let's go back to here. We're now going to create a new variable called party2. And we're going to give it a blank label. And what we're going to do here is we're going to say replace party2 equals liberal if party equals lib. This just makes things a little bit easier to read. Replace party2 equals progressive conservative if party equals p dot c dot. I'll do this for the remainder of the big parties here. The New Democratic Party is the leftist party in Canada, and it was the official opposition in the previous parliament to the one that's running right now. And the last one. Now, sort of the methodological justification for including all of these parties is that each one of these parties has either been a governing party or the official opposition party over the course of Canadian history. So what we're going to do now is we're going to create a new variable called it's called big party, so generate big party, and it's going to be equal to party2, so this new party here, when party2 is not equal to blank. Okay, let me show you why this is the case. If we run our do file with all those changes and we type in br party2, we can see that there are a number of blank observations. Those are all of the original parties. Okay, all of the smaller parties. Here we go. We can see them here. So, and we can just, have those in the. We can basically remove those from the data set or from our new party of big party by not including them there. So, let's do that. Now, isn't that interesting? Something wrong there. There shouldn't be only 3 real changes. What I want there, let's take a look. what I have here is replace party 2 equals Conservative Party of Canada if party equals cons dot. But that's not what that is at all, because there were certainly more than three members of the Conservative Party of Canada. That was the last governing party of Canada, so this is a good teaching opportunity. Let's go through and see what's going on there, that I've picked the wrong party. So tab party 2. Oops, what is tab party? Here we are. And it's not the cons party, it's the C party that I want. That's the new Conservative Party. So let's change the cons to C. There we are. Better. Rerun it. And now we can do create our new big party equals party, where party does not equal blank. That means does not. And that will give us a new dichotomous variable for big party versus not big party. So let's label that, label variable big party, and we'll call it established party. Okay, good. So let's see what this looks like. And if we do tab big party, there we are. So we have values of 1. Oh, what has happened here? Another problem. BR party big party. I don't know why. It's because that should be party 2, not. There we are. Let's try it this time. And tab big party. There we go. That's better. Okay, fantastic. And there are our major party people here, and obviously you see they are the dominant MPs in the Canadian legislature. Excellent. Okay, so let's run a new multiple regression now. Okay, let's run a multiple regression that has a bunch of additional variables. So we're going to do run an OLS, and we're going to do regress vote share, because that is our dependent variable, and then elections contested. That's kind of our incumbency measure that we're using here. And then we'll throw in a couple of other things that we know have an impact on vote share, whether or not the MP is switched, whether or not they are a cabinet minister, okay, whether or not they are a member of a big party, whether or not they are an independent. We're also going to look at how much the party won in their province. Maybe they were riding on a wave of support for their party in the province. So we'll do party prov share. I always include some type of gender variable, so whether or not they are a woman or not, the MP, and we'll also record their experience in years, okay, which is going to be correlated with elections contested, of course. We might have to drop one of those. We'll run a PW, actually we'll run the PW core right now. So PW core, elections contested, and experience. And we can see that it has a really strong correlation, a correlation coefficient of 0.93. So, and if we put sig on the end of that, it's statistically significant. So because those two variables are correlated with each other, it'd be really hard, and they're in effect measuring almost the same thing, right? And how long you've been in Parliament, because the experience variable simply records the number of days or years that you have been an MP. Elections contested is recording effectively the amount of time that you have been an MP as well, by looking at how many elections you have won. We really need to drop one of these variables from the data set. So we'll drop the experience variable right now because we put so much effort into our elections contested. And if we do that, then we can hit enter and see what happens. All right, so here we have our regression output. Okay. And right away, what you can see is that, just a quick glance at the R squared shows that these variables altogether are explaining 43% of the variance in the dependent variable in vote share. We can see that for elections contested, it's still only having a very small effect, but it's still statistically significant. But we can see that if you switch your parties before the election, we can see that your percent of vote share is expected to drop by 7%, and that's also statistically significant. If you're a cabinet minister, you can have an additional 2% on your vote share added if you are a cabinet minister. If you are a member of a big party, you see that your vote share actually drops compared to people who are members of not big parties, right? Beg your pardon. And the reason for this, there might be some correlation going on here too, but we might need to disentangle that. But the reason for that, if you think about it a little bit, is that if you are successful as a member of a small party, it might be because you have captured some type of niche. It might be because you have a very strong level of personal vote in your constituency that you can actually avoid having to be part of a big party in order to ride that party's wave into Parliament. So you have a high degree of independence, if you like, and it's your own personal ability to pick up the vote. So if you are not a member of a big party and you have been elected, you've successfully got in, it's because you're doing something right, and you're actually a stronger contender as a member of one of those smaller parties, having gotten through the hurdle of getting into the Parliament, that actually compared to a big party, you get more votes. So if you look at just big party being one, you see that they have a smaller effect than a lower effect than those who are able to run in a smaller party. This is amplified even more for independents, okay? So who are getting into Parliament, they're getting elected into the legislature, and you can see that independents, if they are successful, let's face it, most independents are not successful, but if they are successful, they are big successful. Okay, you can expect the independents who can successfully get themselves elected into the legislature have vote shares which are 15% higher than non-independents. We see that the party provincial vote share, for every percentage point increase in the party's share of MPs in the province, basically has a positive effect. There's a positive relationship that increases. And for female, we see that if you are a woman, your vote share drops, but it's not statistically significant. So we are unable to reject the null hypothesis that that slope is actually zero. And then the constant, the alpha. So when everything else is at zero, the point where the regression line crosses the y-axis, all else equal, you should just expect MPs, when considering this, MPs to have a vote share of 23.56%. All right, that's a pretty neat model. I'm just going to run it again without big party in there and see what happens, because big party might be PW core and big party and independent. Oops. Keeping in mind that independent these are both dichotomous. Well, it's not. It's a moderate. It's a moderate correlation, so we could probably leave that in there. Okay. And then we'll just run that regress command again so we can see it. There we are. Excuse me. All right. So at this point in the analysis, we should probably run a couple of diagnostics. So let's do that. And so at this point in the analysis, we should probably run some diagnostics. So the first thing that I'm going to do is I'm going to look for outliers. Okay, it's not hard to do. All right, so we're going to use the predict command. We've run the regression command, and you have to run that regress command first before you look for outliers. So we're going to do predict R and R student. Okay, so let's take a quick look here. So that doesn't really going to do. If we just type in the command, it's just going to save a variable called R into our data set, which is going to record the studentized residuals. So now we can take a look at what that looks like, as we'll do a histogram of R, and we'll name that figure 4. Replace, and let's take a look. Okay, so normally distributed, which is a good thing, but we could see that there are, it's very flat over here, but we could see that there are some outliers here over at the edge, and there's an outlier over here at the edge. And so we might be thinking to ourselves, are these particular outliers causing any kind of distortion in the regression analysis? So let's take a look at who these guys are. Okay, so if we want to see who these particular individuals are, we can simply sort R, the variable that was created by Stata for looking at the size of the residuals, and we can look for the highest and the lowest values. And if we know something about our case, we should be able to identify who those people are and then make a judgment call as to whether or not we need to remove those observations from the data set. So let's do that. Let's do sort R. You can see there's the studentized residuals down there, and then we'll do BR, where I want to see who they are, and so we'll do name, and actually it's not name, it's candidate, and we'll do the election, just in case it was a weird election. We'll look at their vote share, and we'll look at their party. The thing we'll probably want to take a look at is these people might also be people who were acclaimed, right? So people who received 100% of the vote share because they were the only person running. And let's take a look at who these people are. So there's vote share. Oh, where's R? We forgot to include R in there. Okay, so for our very, very low levels, we have Charles Perron, Robert Ryan. I'd have to look up who these people are, but they don't stick out to me as particularly significant individuals. But let's take a look at the people who are right up at the top there. Okay, here we are. Okay, so right away some things are sticking out for me right now. First of all, we can see that we've got 3 people here who secured 100% of the vote because they were acclaimed, so they ran uncontested. Sheila Feinstone actually inherited Pierre Elliott Trudeau's seat when he retired, and so that is one of the safest Liberal ridings in Canada, and so you can see that she had a very, very high vote share. Pierre Cardin was a cabinet minister, but also Pierre Cardin split off and formed his own party. That's why he's an independent there. And so when he split off and ran his own party, he had a high level of support in his constituency. So that's actually a legitimate size for his vote share. He was sort of following constituency demand over conscription in the Second World War. So he was French-Canadian from Quebec. And a lot of Quebec opposed conscription in the Second World War, and so he split off from the governing Liberal Party and formed his own party in Quebec, which was anti-conscription. So that's probably legitimate there. Lucien Lamoureux was he was the Speaker of the House, and there's a tradition in Canada that the Speaker of the House, when he runs after stepping down as Speaker of the House, runs uncontested. But in this case, what ended up happening was one party decided not to follow convention and challenged him. He still won, overwhelmingly, but that's the reason why that's not a 100% support there. Here you have Pierre Trudeau, obviously one of the more popular prime ministers of Canada. So these are all probably legitimate examples of people who have high vote shares and are over on the edge and would be found to have seen to be outliers, but the outliers are legit. So I think we could probably leave those particular instances in the data set without having to take them out. They're also very few and far in between, and they shouldn't be distorting the data set very much, given that there's such a high n in that data set. Okay, so we can leave that where it is. We might also want to take a look at whether or not the see whether or not the residuals are randomly distributed along the regression line. Okay, because remember, one of the things that we need to know with regression analysis is that the residuals, we don't have evidence of heteroskedasticity. That is, the residuals are clustered on one side of the regression line or on the other side of the regression line. What we want to see are residuals around the regression line that are randomly distributed, that show no real distinctive pattern. So let's run a diagnostic to look at that. And okay, so to do this, we can use a residual versus fitted values plot. You would have remembered this from my earlier lecture, and that's a RVF, residual versus fitted plot. And we're going to set it up so that there is a horizontal line where the regression line is. Now remember, what this plot is doing is it's basically taking the regression line, it's flattening it out so that it is on a horizontal axis, and then you can see how the residuals are above and below that regression line. So we will just do y line 0, which is going to put a horizontal line at the point in the y-axis where it is 0, which is going to be the regression line, and then we can see how far above and below the residuals are from the regression line. We'll also save that plot into memory. So name figure, I'll call that figure 05, replace. Okay, and much like our previous graph there, what I'm going to do is I'm going to change the size of the dots and make them hollow circles. So I'm going to do M size. I could do this in the pull down menu if I wanted to, but I can just type it in now. Medium, and then we're going to change this. That's going to change the size of the dots, and we're going to change the symbol to being a hollow circle, or I'm going to change it to being a point. Okay, so M symbol, and it's going to be point. Because there's a lot of observations in this data set. There's over 7,000 of them. So if we have a bunch of hollow circles all over the place, it's just going to fill up the screen and make it look really ugly. All right, let's see if that works. And there's our histogram from the studentized residuals. And there we go. Okay, there are all of our 7,000 observations. And you can see there's our line. That's our regression line. So imagine that this graph has actually had the regression line going slightly up. We've just flattened it out. We're looking at how the residuals are scattered around that regression line. And one of the things we can see is that actually it looks like the residuals are expanding over here a bit, and they've expanded up here a bit. There's a couple down here. So just visually looking at this, there seems to be a bit of evidence of heteroskedasticity. We would rather see all of those dots being nicely randomly scattered all around the line. But you can see there's some open space over here, some open space over here and there, and over here. And that kind of gets me a little bit worried that there might be evidence of heteroskedasticity, that the residuals are not randomly scattered around the regression line. If we wanted to actually run a test for heteroskedasticity, there is a test for it, and it's called just a heteroskedasticity test. And to run that test, you can just do est at het test. Het test is for heteroskedasticity test. And if we do that, we just rerun it. We'll get the graph again. I should have commented that out. So there's our residuals, there's our residual plot against the fitted line. If we close that and take a look, we could see that. So this is the Brush-Pagan-Cook-Weisberg test for heteroskedasticity. HO suggests that there is constant variance throughout here, and we want so that there is no heteroskedasticity, and we've run a test where we're rejecting the null hypothesis that there is no heteroskedasticity, which suggests to us that there is. So we need to do something to our regression command in order to squish those residuals so that they are closer to the line, and deal with this heteroskedastic problem. And the way to do that is very, very simple. In Stata, we will simply rerun our regression analysis. So we're going to cut and paste our OLS, and we'll do rerun regression while controlling for heteroskedasticity and using robust standard errors. And so we do that by running regress, all of our variables, and with the extension at the end called robust. Run that again, and that should squish our squish our standard errors to eliminate the heteroskedasticity. And what it's going to do is we have our new regression output here. The coefficients remain the same, but what we have is the standard errors get a little more squished thanks to this robust command. And that's our model. Okay, so that should get you through here, and that provides you with a very nice story of what we can do with the regression analysis. I hope you found this helpful, and if you have any questions, by all means, feel free to contact either myself or Katrine, and we'd be happy to elaborate on any of these elements. Thanks very much. Bye.